Well, in our next section of Chapter 14, we're taking a look further at alcohols, this time investigating the reactions involved in an alcohol functional group. And the first of these will be called dehydration. And think of dehydration just as you might think relating to water. To dehydrate means to remove a water molecule, so loss of a water, HOH. To dehydrate is the loss of water from whatever starting material we are looking at in terms of reactants. We're looking specifically here at alcohols. To force this dehydration, we need some sort of a catalyst, some sort of input of energy, and that is coming from a strong acid such as sulfuric acid called battery acid, H2SO4. So the criteria for a dehydration, I want you to think of water as HOH. The OH is going to be coming from the alcohol functional group, and the hydrogen has to come from a neighboring carbon. So for example, the first carbon is attached to a hydroxyl group. That's our functional group called the alcohol. The second carbon is an adjacent carbon, and we're looking at one of the hydrogens attached to that adjacent carbon. When we take off an H in OH, these bonds collapse and we form a double bond between the two carbons. Removal of two single bonds notice two bonds are being broken, a single bond to carbon hydrogen and a single bond to hydroxyl, the OH, removing two single bonds to form one double bond in an alkene functional group. And that double bond will occur between the two carbons that originally had the hydroxyl and the hydrogen removed. So this is an example of an elimination reaction. Parts of the starting material are lost and a multiple bond is formed. In this case, the multiple bond will be a double bond, the alkene family, ENE. So when we look at dehydration, the loss of a water molecule, carbon number 1, this would be called ethanol. Carbon 1 contains the hydroxyl group. That's our functional group called an alcohol. Carbon 2 has the adjacent hydrogen that's going to be removed. So we need an adjacent hydrogen next to the carbon that's attached to the hydroxyl group. We break these single bonds and form a double bond between carbon number 1 and 2. Removing an HOH is a dehydration. Water is the product, and now we've formed a double bond in what was once a saturated hydrocarbon. Even in a cyclic structure, carbon 1 is attached to the OH, the hydroxyl group. This is the alcohol functional group. The adjacent carbon must have a hydrogen so that when we eliminate the H in the OH, out comes a water, and we create the ene. The cyclohexene has now formed a double bond where there once was a single bond between the carbons. Those particular examples had very symmetrical outcomes. In other words, if I go back a slide, do you see, had I really just decided to take this hydrogen, that it's an equivalent hydrogen in either direction? That had I, just thought about taking a different hydrogen in the opposite direction, it would have put our double bond here. But that's the exact same structure as this. These are equivalent hydrogens. So what if we have a situation where I can form two different types of structure? And let's look at 2-butanol. And I'm going to just draw this with you. Let's put together on our page 2-butanol, meaning that the hydroxyl group is coming off of carbon 2. And I'm going to just take a moment and draw in the hydrogens so that we clearly see all of the H's in this structure as well. All right, we named this 2-butanol. Now, in a dehydration, this is an elimination, you're going to have a strong acid sitting on top of the arrow. We locate first the hydroxyl group, right? This is what we're eliminating, the OH. The carbon that's attached to the OH is involved in making the double bond. It must have an OH to make water, right? We got to take an OH to make HOH. But I noticed the adjacent carbon to the left has a hydrogen, and the adjacent carbon to the right has a hydrogen. So I can see that I can consider eliminating HOH from the green, or HOH there from the bright pink hydrogen. So what will we make? Well, let's first do the bright pink one. 4 carbons in a row, and I'm going to eliminate the HOH, and the double bond then would form between carbon 1 and carbon 2. Or and this is the elimination from hydrogen carbon 1. Eliminate C1 hydrogen with C2 alcohol. All right, so we eliminated the OH from carbon 2, the H from carbon 1, and remember that you split out a water molecule as the other product. So one possible product is 1-butene. What if, in the presence of this sulfuric acid, we eliminate the bright green hydrogen that's between carbon 2 and carbon 3? So here we have 1, 2, 3, 4 carbons. Carbon 2 had the OH, but carbon 3 has an adjacent hydrogen as well. So this time we're going to eliminate the C3 hydrogen and the C2 hydroxyl. And when we do so, we put the double bond between carbon 2 and carbon 3. We made 2-butene. Those are 2 very different compounds. They are constitutional isomers. They're connecting their atoms in a different way. One of them places a double bond between carbon 1 and 2. The second places its double bond between carbon 2 and 3. They have unique names, so they're unique compounds. 1-butene versus 2-butene. So which one does it make? And that's going to just slide up here. I'm just wanted to show what we were looking at. If I eliminated a hydrogen from the first position, we made 1-butene. If I eliminated the hydrogen from the third carbon, we made 2-butene. And there is one preferred product over the other, and that's going to dominate from Zaitsevs' rule. The major product of an elimination reaction puts the double bond on the most substituted branches. The major product has the most alkyl groups bonded to the carbon double bond. Let's put that into better picture here. 1-butene. When I think about what's bonded to 1-butene, I have a C, double bond C, and this is how it came out, 1-butene. 2-butene placed the double bond between carbon 2 and carbon 3, and so the branches looked like this. That just happens to be cis, it could be trans, it doesn't matter, but the connection there does. If you find the double bond and just kind of highlight where the double bond is located versus this double bond, which one has more carbons coming off of the carbons in the double bond? Which carbon, which way is this structure have more carbon attached to the double bond? You want more branches on the carbons in the double bond. And clearly, after I get that all written out, this has 2 branches coming off, whereas this only has 1 branch. This is mono-substituted, whereas this is di-substituted. So the major product is the one that places more carbon branches on the carbons in the double bond, which is 2-butene. So the major product, 2-butene, over the least substituted branched alkene of 1-butene. That's called Zaitsevs rule. Let's do another practice together. Here it says, draw all possible elimination products and then determine which one will be in the majority. So here I have a carbon attached to carbon 2 in a 5-membered carbon. So just kind of think that through. 1, 2, 3, 4, 5. And then this carbon has another branch, right? Carbon 4 has 2 methyl groups coming off of it. 5 carbons, carbon 4 has a methyl branch. Carbon 2 has the OH. So look adjacent to the carbon on the OH group. Who's adjacent to that? And let me color code those as well. I'll make this particular carbon all red hydrogens. And over here, I'll make these blue. Alrighty. There are more hydrogens, but those are the ones that are available for elimination. I have to eliminate the OH and a hydrogen from an adjacent carbon. So you'll see on the arrow H2SO4, a very strong concentrated acid to force dehydration. Now let's eliminate a red hydrogen first. We're going to eliminate OH, and when we do so, the bond collapses and the double bond will go between carbon 1 and carbon 2. And I made that structure red on purpose so that you could see the double bond between carbon 1 and 2. Now let me go back to the blue color coding. If we had taken OH and H and eliminated the adjacent hydrogen from carbon 3, then we would end up with a double bond between carbon 2 and 3. 1, 2, 3, 4, 5. So carbon 2 and 3 now contain the double bond. Keep in mind, we're splitting out water, so always the second product writing out there is plus H2O. Which one is going to be the major product? The major product comes from finding the double bond. Where do you see the double bond, and how many substituent branches does it have? How many other carbons are coming off? And so I'm locating the double bond. The more branched the double bond is, the more stable the configuration. So here we would have the major product, and we could name that as 4-methyl 2-pentene, a 5-carbon ring where the double bond is located between 2 and 3 on the carbon chain. Zaitsevs rule, the major product has more carbons coming off the carbons in the double bond. Here we had no carbons coming off of that carbon, and here on either side we had 1 carbon coming off of each carbon that's in the double bond. That's the winner. Zaitsevs rule. Draw the products formed when each of these alcohols is dehydrated with H2SO4. We locate the carbon on the hydroxyl group. Then we locate the hydrogens in the adjacent position. To eliminate, we need an adjacent hydrogen next door to the hydroxyl group. Now these are equivalent hydrogens. I mean, they're exactly the same direction, right? So it wouldn't matter if I eliminated in this direction because I still produce one propene. That's me taking one hydrogen and this OH and the bond collapsed there. Or even if I had taken this adjacent hydrogen, you still would end up with one propene. Those are equivalent hydrogens. So nothing to choose from there. They're the same overall. Here we have an aromatic ring and 1, 2 hydroxyl. All right, so 2 there and then the hydroxyl group. So really, again, I only have one choice. There's only one adjacent hydrogen. So there's my aromatic ring leading to carbon 1, carbon 2, and this is where the OH is. So the adjacent hydrogen is only one. So as I think about eliminating an HOH, the double bond would form here. And don't forget, always there's a plus water. Dehydrate, remove water. So you have your aromatic ring with alternating double single bonds, then leading to a carbon to carbon double bond. So that's plus water. And letter C, this carbon is attached to the OH. So the adjacent carbons are again equivalent. Adjacent carbons in either direction are the same. So I don't really have to choose. Here I have a cyclopentane, that's a 5-membered ring. This carbon and this carbon would form a double bond, which is identical had I taken this one. The double bond would have just landed, instead here. And so it would have fallen here. Those are the same compound. Alrighty, so no need really for any of those to use Zaitsevs rule because each hydrogen that we selected had an equivalent. If there were more than one choice, they were equivalent choices. But what about a situation where I would have to draw more than one structure? Perhaps these show us that opportunity as well. So again, here's a cyclobutane 4-membered ring. This is the carbon attached to the OH. I go in either direction to find an adjacent hydrogen, and those two are equivalent positions. They're not different from each other. They're absolutely the same. And so I can remove any of those and place a double bond between carbon 1 and 2. Cyclobutene would form. Here I have a secondary alcohol. The carbon attached to the oxygen there is attached to 2 other carbons, so it's secondary alcohol. This carbon is 1, 2, 3, 4 bonds. Do you see that that has 4 bonds already, all leading to carbon? So therefore, there's no hydrogen. Therefore, there cannot be an elimination at that particular spot. So when I think that through, the only place for hydrogen is in this direction. Those are both H's available for dehydration. But there is no hydrogen if I went left on that chain. There's 4 bonds on this carbon already. All are leading to carbons. So there's no hydrogen. We can't eliminate H from a carbon with no H on it. So when I draw this product, the aromatic ring leads to a carbon. Notice there's 1, 2, 3 carbons in that chain. 1, 2, 3 carbons in the chain, but the H and OH have been removed to form an alkene, splitting out a water between HOH from carbon 1 and 2 on that propyl chain. Here I have a carbon at number 2 and a longer carbon chain that looks like it's 6 carbons long. I can tell I have some choices here finally. There's an adjacent carbon with hydrogen in that position, and there's an adjacent carbon with hydrogen in that position. I can look left and see available carbons, and I can look right and see available carbons. Using Zaitsevs' rule, I understand that the hydrogens that are going to produce more carbons on the carbons in the double bond, that's more branched, has more substituents, will be favored. So I'm going to eliminate hydrogen off of carbon 3 to create the more branched hydrocarbon. So let me put my 5, nope, there's 6 carbons, 1, 2, 3, 4, 5, 6. The double bond ends between carbon 2 and 3, and there is our elimination, 2-hexene. 1, 2, 3, 4, 5, 6. Between carbon 2 and 3 is a double bond, 2-hexene for letter C. And letter D. So here I have the carbon that's attached to the hydroxyl group. I'll call that position 3. It looks like I could get that there from either direction. Carbon 3, there's a hydroxyl. I have actually some interesting choices because I have an adjacent hydrogen here. I have an adjacent hydrogen here and adjacent hydrogen there. Those two happen to be equivalent because they're both attached to one other carbon. 1, 2, 3, 4, 5. Carbon 2 and carbon 4 are equivalent. But this methyl group is not equivalent hydrogen, but it would not lead to the most substituted hydrocarbon. So I'm going to draw my 5 carbon chain. I know at carbon 3, this methyl will still be there because those hydrogens don't produce the most substituted double bond, but I can place it between carbon 1, 2, 3, 4, 5. I'm going to eliminate the hydrogen off of carbon 2. And when I did so, I put the ene, that double bond, between carbon 2 and 3. And you clearly see that had I done the other direction, I ended up with the exact same compound. So there's 5 carbons in a row. Carbon 3 has a methyl, and if I had taken that hydrogen, I still ended up with 2-pentene. Zaitsevs' rule, make sure your double bond is in the most substituted position. This is kind of interesting, working backwards. What alcohol is needed to form an alkene if this were the product of a dehydration? So we're working backwards, right? I'm kind of pointing this and asking, what was the starting material? So remember, you want to break the double bond and just add back H and OH. So with letter A, we'll draw our 6-membered ring. It's aromatic, leading out to a carbon. It will now be single bonded, and I'm just selecting adding back an HOH, and we lead out to a mirror image. So it really did not matter which carbon received the H or OH. It's a perfectly symmetrical molecule. Those are 2 equivalent carbons. Same thing here. This is a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. So my structure will start with an 8-membered ring. This is not going to be pretty. 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's not so bad. Good job, Linda. And I'm going to add an HOH back across the double bond. And remember, I don't have to be drawing these H's. I can choose to leave them off. So if I erase this, it's still correct. If I erase this, it's still correct. I have an alcohol as the starting material. Other types of reactions that alcohols undergo include oxidation and reduction. Let's remind ourselves what those two terms mean. Oxidation. When we increase the number of carbon to oxygen bonds in a hydrocarbon chain, we are oxidizing. Another way of saying that is to decrease the number of carbon to hydrogen bonds. You are oxidizing. So for example, if I have the alcohol functional group, the OH alcohol functional group, and the adjacent hydrogen, if we break two single bonds to form a double bond, we've increased the number of carbon to oxygen bonds. That's called oxidation. Notice here in the beginning material of an alcohol, we have just a single bond of the carbon to oxygen. To oxidize means we're going to increase the number of bonds. Well, increasing that goes from a single to a double bond between the carbon and oxygen. We've added a new CO bond. We've decreased the number of CH bond, and we've increased the number of CO bond. Both of those terms are what we call oxidation. We'll now know that this functional group, the C double bond O, represents a carbonyl group, C double bond O. An alcohol, when it's oxidized, turns into a carbonyl functional group. You need a pretty powerful oxidizing agent to do so. We typically use a common salt in the lab to do so, K2Cr2O7. If you remember your polyatomic ion chart, this is called potassium dichromate, a polyatomic ion called dichromate, Cr2O7. Carries a -2 charge, so that's why we need two positive potassiums to electrically balance the -2 dichromate charge. So you'll commonly see that as your oxidizing agent. Alcohols are oxidized to produce carbonyl carbons, and if we continue the oxidation process, we can actually go all the way to a carboxylic acid. If the carbon attached to the hydroxyl group is attached to two other hydrogens, we call that a primary alcohol. The carbon is attached to just one other carbon, that's primary, meaning it has two carbon to hydrogen bonds that can be oxidized. If we break one bond from the C to the H, and increase the number of bonds to carbon, increase the carbon to oxygen, because we went from a single to a double, that's increasing the CO bonds. And we've eliminated one of the C to H, that's also called oxidation. We went from an alcohol to an aldehyde. The aldehyde has that carbonyl at the terminal end. And in a next step, I can add even another bond and go all the way to form carboxylic acid. This example would show acetic acid. This is very critical. Primary alcohols, under the first oxidation, form an aldehyde. Under the second oxidation, form a carboxylic acid. You need to know that. Somehow, this is a big important spot in your notes. Alcohols oxidize, if they're primary alcohols oxidize to aldehydes, and then one more step, because it has a remaining hydrogen here, one more step is possible, going all the way to a carboxylic acid. Only true for primary alcohols, because it's the only type of alcohol that has two bonds from C to H, are the primary positions. Secondary alcohols, that means there's a carbon attached to two other carbons and only one available hydrogen. That means when it's oxidized, it only has one available hydrogen to eliminate and form a bond to oxygen. Secondary alcohols form ketones. That's it, because there are no more hydrogens to eliminate. And look at here, this is a tertiary alcohol. Tertiary alcohol says, oh, this is 1, 2, I'm sorry, this is still a secondary. I jumped a screen in my mind. That I have a secondary alcohol, meaning that that carbon is attached to just 2 other carbon, and we formed a ketone. The ketone is R carbonyl carbon and then an R chain. Ketones. Now, what about those tertiaries? Remember that a tertiary alcohol is defined as the carbon is bonded to carbons in all directions. There are no available hydrogens, therefore no reaction. Tertiary alcohols cannot be oxidized. There are no hydrogen bonds to break. Primary alcohols form an aldehyde to a carboxylic acid. Aldehyde to a carboxylic acid. Secondary alcohols go to a ketone and stop. Tertiary alcohols have no reaction. We must know that. Let's practice. We're going to use potassium dichromate. You sometimes just see that as an oxidizing agent sitting over an arrow. If you see a bracket with an O, it just means an oxidizing agent. Sometimes there are no reactions. What products are formed when each alcohol is oxidized by a strong oxidizing reagent such as potassium dichromate? Letter A. Letter A gives me 2-pentane-ol, a 5-carbon chain. That 5-carbon chain has an alcohol on a carbon that's attached to 2 other alcohols. We call this a secondary alcohol. And that tells me when I eliminate from a secondary alcohol, we know that that is going to produce a ketone. So the hydrogen bond that is broken, right, is the one that's attached to the carbon. So let me emphasize, it's not an adjacent carbon in this chemistry. It's on the same carbon. That's the one that's going to be eliminated. And in doing so, you form a double bond to the oxygen. So carbon, 1, 2, 3, 4, 5. The oxidation, you can just see that is putting a little arrow and then the term oxidizing agent, K2Cr2O7, or just an O in a bracket to represent oxidation. The hydrogen bonded to the carbon that's part of the hydroxyl group is eliminated, and you create a double bond to the oxygen. So this is a ketone functional group. A secondary alcohol produces a ketone. How about letter B? 1, 2, 3. So it looks like I have 3 carbons, and then this carbon here is attached. 1, 2, 3 carbons is attached to 3 other carbons like this. There's our structure, and then the OH is here at the end. So that means this is a primary alcohol, meaning I have 2 available hydrogens on that carbon. So when I oxidize, I eliminate the hydrogens that are on the same carbon as the hydroxyl group. So in the first oxidative process, the primary alcohol goes to an aldehyde. And that means at the back end of the molecule, still the same, leading to an aldehyde. We've eliminated 1 CH bond and formed a double bond known as a carbonyl functional group, C double bond O. But notice that I still have a hydrogen that I can eliminate here, right? I can still eliminate that CH bond and form one more oxidative process. So there is a next step where I still have the tail end the same. Now this carbon is eliminating the H at the terminal position and going all the way to a carboxylic acid. Cool. Secondary alcohols have one oxidative process. Primary alcohols have two oxidative processes. So you're going to see two sets of arrows for primaries. Letter C, a cyclopentane, 5-membered ring. And there's the alcohol group. So that means the carbon that's attached to the hydroxyl has just one hydrogen to make its fourth bond. That is what we call a secondary alcohol. When it undergoes oxidative process, there's only one available hydrogen to eliminate the bond from. And when it does so, it forms a ketone, and we're done. Secondary alcohols undergo oxidative process. I'm trying to write ketone. Yeah, there we go. A double bond out from where originally we had the alcohol. And letter D, did you notice this carbon is already bonded to 1, 2, 3 other carbons? It's a tertiary alcohol. There are no hydrogens there, so no reaction. Tertiary alcohols cannot be oxidized. You need some practice, I know, so just make sure you're giving yourself enough repetitions to make this easy. Draw the products formed when each alcohol is oxidized. Do you recognize if it's primary, there's two oxidations? If it's secondary, there's one oxidation. And if it's tertiary, there are no oxidations. Alrighty. So here in letter A, I notice that I have a long hydrocarbon chain. It's 1 plus 6 is 7. There's 8 carbons in a row and then an OH group at the end. 1, 2, 3, 4, 5, 6, 7, 8. There's the OH. This is a primary alcohol. That means there's 2 hydrogens available to be oxidized to increase the number of bonds to C to O. In your first oxidative step, 1, 2, 3, 4, 5, 6, 7, 8 in a row, that carbon here now is going to form a carbonyl and end at an aldehyde. So I did 1, 2, 3, 4, 5, 6, 7, 8, and created the aldehyde. There is a second oxidative state because there's still one more hydrogen that we can eliminate. 1, 2, 3, 4, 5, 6, 7, 8. We still have the carbonyl, C double bond O, and now we go all the way to the carboxylic acid. That's cool. Carboxylic acid for a primary alcohol is the ultimate end of our oxidative process. Primaries will make an aldehyde and go on to form a carboxylic acid, COOH, at that terminal carbon. Letter B. This carbon is attached to a hydrogen attached to an OH, and then it has 2 groups of ethyl. So this is the structure for letter B. This carbon attached to an H and OH and 2 groups of ethyl. So this undergoes one oxidative step. So this will be a secondary alcohol. going on to form a ketone. There's 3 carbons in the longest chain, and right here becomes the ketone. Okay, letter C. 1, 2, 3, 4. 4 carbons in that chain. The carbon that's involved in that oxygen is a primary. I see 2 hydrogens there, so we have 2 steps to go through. So letter C. 1, 2, 3. This now will lead out to a carbonyl. This has a branch. There's still a hydrogen there, so the first product is the aldehyde. And then this will undergo a next step where the aldehyde converts to the carboxylic acid, so we see an OH at the end, and still that branch up there. So we went from primary alcohol, in letter C, a primary alcohol, to an aldehyde, to a carboxylic acid. And letter D, notice that the carbon is already filled with 4 bonds, a tertiary alcohol, so no reaction. Doing great. You now have an assigned reading on section 6, focus on health and medicine, the metabolism of ethanol. And I'm just going to ask you to do that part in your notes, kind of just go through that reading and pull out some important or interesting information to fill in your notes over section 6, health effects, health and medicine. And then come back and start your last part of the lessons. We'll look at ethers, and we have alkyl halides. And we still have thiol groups left in our journey ahead. Do a little reading and come on back.